There is a day on your calendar that looks perfectly harmless. It sits there like all the others, a small box, a quiet number buried between appointments and unread notifications. Your weather app shows a bright little sun beside it. Your alarm is set. Your plans are ordinary. Somewhere between scrolling and sleep, your eyes slide over that date without stopping, the way they have for every date before it. But not all days wait politely to arrive. Some days lean forward from the future. They gather weight long before your clock ever reaches them. They begin not when you wake up, but when something else does, something far above your ceilings and your cities, on a surface you never really see. This story doesn't start with a date. It starts with a moment in a dark control room, when someone who spends their life watching the sun noticed that today, the star you think of as steady, wasn't. On their screen, the perfect circle of light you carry in your head was gone. In its place, a rough, grainy surface of boiling cells, arcing loops of fire. And there, stamped into that blinding landscape like a bruise on living skin, a scar. An active region. A sunspot group. A label, AR4294. On your phone, the sun is a friendly symbol. A flat disk. A promise of daylight. Your eyes can't rest on the real one long enough to form a picture, so your mind never does. But through the right filter, on the right day, that symbol shatters. The sun becomes a place, a blinding, seething ocean of plasma, its surface forever breaking and healing, stitched with magnetic fields. On those days, if you walk into a backyard where someone has set up a small telescope with a proper solar filter, they can show you something your ancestors never saw in such detail. Not a perfect white circle. A mottled face. Textures. Grain. And sometimes dark holes where no holes should be. AR4294 appeared that way at first. A dark knot punched into the sun's photosphere. Through smoked glass filters and hydrogen alpha scopes, amateurs could see it themselves. A tiny, irregular shadow on the glaring disk, large enough that, if you could place the Earth next to it, it would look like a small marble beside a black continent. News posts called it impressive, complex, worth monitoring. Websites translated its size into human terms. This region could swallow several Earths. Forecast pages added tidy numbers, a certain percentage chance of strong flares in the next 24 hours. To most people, that was where the story ended. A curiosity. A headline scrolled past. A pretty aurora picture shared that night from someone closer to the poles. But the sun does not care about our headlines. And in the quiet rooms where the raw data arrives without captions, where the star above you is not an icon but a stream of numbers, AR4294 did something else. Something that made people who have seen hundreds of sunspots lean a little closer to their screens and frown in a way you will never see in a press conference. Because AR4294 was not just big, it was restless in the wrong way. To understand why that matters, you have to know what normal means on a star that never truly rests. Sunspots are not stains on the sun. They are knots. They are places where magnetic fields, invisible lines of force rising from deep inside the star, punch up through the surface and dive back down again, looping like ropes thrown into boiling water. Where those ropes bunch together, they strangle the heat trying to rise. The surface cools by a few thousand degrees. It's still hot enough to incinerate anything you've ever touched, but against the surrounding glare it looks dark, like burned skin on an ocean of fire. Solar physicists treat these knots like meteorologists treat storms. They do not just look at them, they measure, classify, and sort. How big is the region? How are the polarities arranged, north and south magnetic fields? How twisted are the loops that connect them? Are opposite polarities neatly separated, field lines arcing gracefully between them? Or are they jammed together, tangled so tightly that the magnetic map looks less like a diagram and more like a bruise? Simple spots are like gentle low-pressure systems. Two clear polarities cleanly divided. They flare sometimes, a small burst of energy here, a flicker there, but they rarely surprise anyone. Then there are the monsters, sprawling delta-class regions where opposite polarities overlap, where the magnetic field looks like someone took an orderly set of loops and wound them until they began to snarl. Those regions get higher numbers in the forecast, a strong chance of major flares, elevated risk of coronal mass ejections, ingredients for serious storms. For decades, this way of looking at the sun has mostly worked. Not perfectly. Not in the way of clockwork. But well enough. You see a simple spot, you expect small events. You see a complex delta region, you expect bigger ones. Satellites can be warned. Power grid operators can be told to be ready. Pilots can be alerted to possible radio blackouts on polar routes. In this way, the sun's misbehavior is wrapped in probabilities. Wild but charted. Dangerous but with labels. At first, AR4294 fits snugly into this box. Large, complex, delta. The models knew what to do with that. The forecasts lit up with their confident percentages. The space weather pages turned their dials to elevated risk. The star above you was misbehaving, yes, but inside a familiar range of misbehavior. Then the data stopped fitting as neatly under the labels. Every day, multiple spacecraft stare straight at the sun, not in the warm glow you feel on your skin, but in the invisible language of magnetism. They produce magnetograms, stark maps where white patches mean the field is pointing toward you, black patches mean it's pointing away. To most people, they look like abstract art. To the people who can read them, they are X-rays of the star's bones. When AR4294 rotated fully into view, its magnetograms looked exactly as you might expect for a monster region. Dense knots of black and white pressed tightly together, tangled edges glowing with complexity, small islands of mixed polarity scattered like magnetic shrapnel around the core. No one gasped. This was what big, dangerous spots are supposed to look like. But magnets do not freeze. Neither does the sun. The instruments kept watching. Frame after frame. Hour after hour. And that is where the unease began. In the standard picture, the most tortured parts of a region slowly relax. Opposite polarities drift apart. Magnetic tension eases. The knot unwinds. That is the sun's way of breathing out. AR4294 did not breathe out the way it should have. Regions of opposite polarity that the models expected to separate instead curled back toward one another, like ink being stirred back into itself. Tiny pockets of reverse polarity, little patches where, briefly, the magnetic field flipped direction, flickered to life along the edges, then vanished, then reappeared, on timescales that felt too fast for the simple layered structure in the textbooks. Field lines, when extrapolated into 3 dimensions by the codes that attempt to reconstruct the sun's invisible scaffolding, remain taut even after small flares that, in other regions, would have been enough to relax them. It was as if the region had its own internal clock, ticking slightly off from the rhythms the usual equations prefer. In lab rooms and mission centers, people scrolled back and forth through those magnetograms again and again, watching that dark scar on the sun's surface change shape. The patterns felt familiar, they had seen knots like this before, and at the same time, something in the way the black and white swirled together whispered wrong. Not dramatically wrong. Not rewrite the physics wrong. But this doesn't quite do what we expect wrong. That feeling is where real stories begin. Where magnetograms show you bones, light shows you breath. High above AR4294, telescopes tuned to extreme ultraviolet and X-ray wavelengths stared into the sun's outer atmosphere. The corona, a tenuous halo hotter than the surface beneath it. Their instruments recorded brightness over time, turning the region's wild flickering into graphs that crawled across screens in real time. At first glance, those plots always look like chaos. Spikes and jitters. Constant noise. The natural agitation of superheated plasma trapped in magnetic cages. But if you compress time, if you stack different wavelengths together, if you squint at the noise in the right way, patterns sometimes emerge. In the case of AR4294, the noise started to sound like a heartbeat. Microflares, tiny bursts of energy that barely disturb anything beyond the sun's immediate surroundings, were not appearing purely at random. They clustered in loose bands of time. Periods where the region crackled more than usual, separated by stretches of relative quiet that dipped under the baseline. It wasn't a metronome. Not a perfect, mechanical tick-tock. But it was rhythmic enough to make some people uneasy. It looked suspiciously like pacing. As if the region was inhaling and exhaling. As if it were taking steps towards something. Some scientists raised an eyebrow and then raised a warning flag. Human brains see patterns in clouds, faces in shadows, rhythms in static. Turbulent systems can easily cough up quasi-periodic behavior without any deeper meaning. They urged caution. Don't romanticize noise. Others leaned in. They began to overlay those bands of heightened microflaring with changes in the magnetic field. Subtle shifts in connectivity. Loops that brightened or dimmed in concert with the pulses. The picture that emerged was not definitive, but it was suggestive. It looked like the region was trying on different configurations, rearranging its internal wiring. A small rearrangement here, a breath of energy there. Over and over, clearing its throat. Watching those light curves, you could get the same feeling you get when you see someone drawing breath before they speak, but they keep stopping as if choosing their words. The bright flashes from AR4294 felt less like the main performance and more like rehearsal. The sense of prelude hung over everything. Then the first major flares erupted. The world noticed the way it always does now. Space weather websites updated. Charts went red. Alerts pinged on phones belonging to satellite operators and power grid managers. Headlines mentioned strong X-class flares from giant Sunspot AR4294, and explained once again what an X-class flare is. From far away it all looked comfortably familiar. The energies were high, but not record-breaking. The sun has hurled stronger flares in living memory, and unimaginably stronger ones in its 4.5 billion-year life. But the people who study flares as carefully as crime scenes saw a different kind of story. They traced the bright ribbons that spread along the sun's surface during each eruption, mapping the bursts of light exactly onto the underlying magnetic field, or rather onto where the model said the field should be. In a textbook flare, the ignition point sits where magnetic opposites are pressed together hardest. The ribbons trace out neat paths along the stressed loops, like lightning following a wire. In AR4294, the brightest flares often lit up just to the side of those expected places. The ribbons curved along paths that implied they were connected to loops the simple extrapolations had not picked as primary culprits. The flare light seemed to move along back roads instead of highways. In some cases, the flare's X-ray brightness rose explosively fast, leaping upward like a match thrown into gasoline. In others, from regions that, on paper, looked similarly stressed, the rise was slow, almost reluctant, as if something was holding energy back. None of this was impossible. All of it could be explained by adding more detail to the models. More small loops, more subtle twists, more three-dimensional complexity. But together, flare after flare, those little mismatches felt like a melody played mostly in tune, with just enough rhythm off that you can't quite relax. The sun was hitting the right notes. It was not playing the song the models had written. From one of those flares, the sun did more than flash. It threw a coronal mass ejection, a vast rising bubble of plasma and magnetic field, peeled away from the region and billowed outward into space. Coronagraphs, instruments designed to block out the sun's bright face and reveal its faint surroundings, captured the CME as a pale, expanding halo. Within hours, software turned that halo into numbers, speed, direction. Early runs suggested a glancing blow for Earth, the kind of event that would bring bright auroras to high latitudes and a moderate geomagnetic disturbance, but nothing world-breaking. Space weather bulletins were written. Time windows were shared. Somewhere on Earth, people made plans to drive north that night and hope for green lights on the horizon. But coronagraphs keep watching too. As more frames came in, the shape of the CME unfolded in greater detail, and the trajectory estimates began to shift. The leading edge appeared to decelerate more than expected. One flank bulged in a way that nudged more of the structure toward the line between Sun and Earth than the neat cone models had assumed. Later, when the cloud finally reached the region of space already occupied by a small fleet of solar wind monitors, their instruments recorded another subtle twist. The internal magnetic field of the CME, somewhere between its launch and its arrival, had rotated into a configuration more effective at coupling with Earth's magnetic shield. In the end, the storm that washed over us was moderate. Auroras flared farther south than usual. Power grid operators saw their monitors wiggle but not scream. Satellites experienced extra drag, a few brief annoyances, nothing catastrophic. Everything was fine. Everything was within expectations. Except the road between launch and impact, the path the storm took through the invisible currents of the solar wind, the way its internal field untwisted and retwisted, had not been predicted cleanly. In the debrief meetings that followed, analysts laid projected tracks over reconstructed ones and felt a familiar sting. We had guessed the destination. We had not truly understood the journey. Down here, wrapped in the planet's magnetic cocoon, Earth reacted in its own complicated way. Magnetometers scattered from the equator to the poles traced curves as the CME pressed against and slid around our field. The main storm phases fit the forecasts reasonably well. A sharp drop at about the expected time, a period of sustained disturbance, a gradual recovery. Those are the pieces that make it into public summaries. The storm peaked around this hour, reached this level on the KP index, and has now begun to subside. But around those main features, like whispers around a shouted word, were smaller disturbances that did not line up as neatly. At some high-latitude stations, brief, sharp spikes appeared hours before the main impact, as if the magnetosphere had flinched at some fine structure in the incoming solar wind that our upstream monitors had smoothed out. Auroral cameras, staring at the polar sky in time-lapse, captured faint arcs racing across the field before the main curtains of light unfurled, structures that, in models, required delicate variations in pressure and field orientation no one had measured directly. The magnetosphere is more than a passive shield. It is its own system, capable of generating storms from small nudges, of storing energy and releasing it in bursts called substorms. It can, in a sense, take a tiny whisper from the sun and turn it into a shout. So perhaps those early pulses, those stray arcs, belonged entirely to Earth's own chaotic magnetotail. Perhaps they were local quirks. But for the people whose job is to draw a line from, this CME left the sun at this time, to, you should expect the largest effects at this time, each unexplained wiggle was another reminder that there are holes in that chain, and that those holes lie between us and the technologies that quietly run the world beneath your feet. None of this makes good television. So the public story stayed simple. AR4294 was a large sunspot group. It produced some powerful flares. It launched at least one CME that brushed the Earth, inspiring auroras and reminding engineers to stay awake. Airlines rerouted a few flights. Satellites took precautions. No catastrophic failures occurred. Life went on. That is what must be said first. Practical impacts, calm tone, reassurance. What rarely gets said outside of technical talks and quietly updated papers is the rest, the list of small, stubborn questions AR4294 left behind. Why did its core rearrange itself on timescales that didn't quite match the models? Why did its microflares pulse in those loose bands? Why did some flares ignore the obvious stress points and ignite off to the side? Why did its CME require multiple rounds of correction in the model forecast? Why did the magnetosphere twitch early in some places and late in others? None of those questions prove a conspiracy. They prove something more unsettling. They prove that the people who know the sun best are still not entirely sure where their certainty ends. By the time AR4294 rotated toward the far side of the sun, carried slowly out of view by the star's 27-day spin, those questions had piled up quietly, like snow in the corners of a quiet street. The physics was not shattered. Magnetic fields still store energy. Reconnection still releases it. Plasma still dance along invisible lines. All the broad strokes held. But the exact way those strokes had come together in this one patch, the way the knot had formed, tightened, breathed, flared, and thrown, had slipped just beyond the edge of the pictures they had been using to think. For convenience, we draw the sun's magnetism as simple loops. We speak of active regions as if they were coherent beings, each with a single personality. We copy diagrams, smooth and orderly, into textbooks and slides. Reality is not obligated to look like our diagrams. Perhaps in AR4294, deep flows welling up from the convection zone were feeding the spot in pulses, saturating it in waves rather than with a steady stream. Perhaps its field contained nested structures our instruments cannot easily see, twisted ropes inside twisted ropes, knots within knots. Most of the time we get away with pretending the sun is simpler than it is. AR4294 was the moment the pretense slipped. When a region misbehaves, the natural instinct is to open the archives. Deep shelves of glass plates from old solar observatories. Early magnetograms, grainy and low resolution. Logbooks listing spot areas and classifications from cycles long gone. Scattered reports of geomagnetic storms before space-age instrumentation. With AR4294 fresh in their minds, researchers combed those records, searching for older regions that carried the same faint signature. Complex, crowded sunspot groups whose flare footprints didn't quite match the maps. Sequences of storms whose timings forced last-minute forecast changes. Subtle, mistimed pulses around otherwise well-behaved events. The data there is thinner. There are no four-dimensional reconstructions. But hints emerged. A handful of regions from previous cycles that, if watched with modern instruments, might have looked like AR4294's older siblings. In their time, those active regions passed as curiosities. That odd storm in 19-something. That weird spot that didn't flare quite the way we thought. The pattern was too faint to see. Seen now, stretched across decades, the pattern sharpens. Maybe AR4294 is not unique. Maybe it is simply the first of its kind we have watched closely enough, with enough cameras and codes, to realize that the boxes we use, simple, complex, delta, safe, dangerous, have always been too blunt. And if those boxes are blunt, then so are the numbers we build inside them. Space weather forecasts are full of digits, probabilities, indices, confidence levels. They feel solid. They guide real decisions. Power companies decide when to hold back. Satellite teams decide when to shut down subsystems. Airlines decide whether to reroute. The aura of precision is useful. But behind it lies an uncomfortable truth. All those numbers are trained on a painfully small sample. We have had continuous, high-quality solar monitoring for only a few decades. We've recorded a few truly strong storms in detail, a larger handful of moderate ones, and a cloud of smaller events. The rare giants, storms on the scale of the Carrington event, we know mostly from the scars they left in other things. Spikes in certain isotopes in ice cores, strange telegraph failures in the 19th century, scattered reports of auroras seen near the equator. AR4294 did not join that list of giants. But it pressed gently on the thinness of our statistics. It slid just far enough against expectations, just far enough along the edge of predictability, to make anyone paying attention ask. When we say, once in 100 years, how much of that is knowledge and how much is hope? While those questions floated in conference rooms and journal drafts, the metal and silicon ring around our planet continued its silent conversation with the star. GPS satellites high above the atmosphere nudged their timing and corrected for the way charged particles in the ionosphere distorted their signals. Communication satellites, detecting increased radiation, rotated sensitive components into safer orientations. Instruments logged their own discomfort in ways you will never see in a news story. A bit in memory flipped here, corrected instantly by error coding, but recorded in a log that will someday be compressed and archived. A guidance computer rebooted there, a brief moment of silence filled with contingency procedures, later filed under likely radiation-induced upset. Low-orbit satellites experienced slightly more drag than the atmospheric models had anticipated, hinting that the upper atmosphere's response to the storm was more structured, more patchy than the smooth gradients in the code. Individually, these events are trivial. Together, they whisper that our technological skin around the Earth is thinner than our confidence often sounds. A storm does not need to knock out all the lights to matter. It only has to push a little harder on the edges of what we think we've prepared for, while people who rarely speak publicly about their fear watch dashboards at 3 a.m. and wonder whether this time will be the one that slips beyond the plan. Inside the agencies watching all this, NASA, ESA, NOAA, and others, another kind of weather plays out. Human weather. If they share every nuance, every anomaly, every "this is odd," they drown the public in noise and erode trust. If they strip away all the texture and speak only in smooth, steady phrases, they risk smoothing over reality even in their own minds. In the story of AR4294, you can almost see the unsent drafts. A sentence in an early bulletin. This region has exhibited several unusual behaviors compared to typical active regions of its classification. Later, an edited version. We continue to monitor an active region that has produced several strong flares. Not because someone is hiding a catastrophe. Because the official voice is not allowed to be uncertain unless the stakes are crystal clear. That instinct, to downplay the uncomfortable until it becomes impossible to ignore, is not a flaw of any one agency. It is what people do. With medical tests, with small, strange aches, with relationships, with stars. AR4294 did not break that instinct. It pushed against it, slowly, finger by finger. The sun itself, of course, knows none of this. It does not know your flight plans or your grids. It does not know what AR4294 means to you or to anyone. It does not have an about page. It burns according to equations that do not include our names. That indifference is strangely comforting and quietly terrifying. On the timescale of a star, the episodes wrapped around AR4294 are nothing. Small storms. Tiny rearrangements of field lines in one of countless active regions on one ordinary day in the life of a yellow dwarf. For a civilization that has built wires, satellites, and stories around that star, those small events are everything. They are data. They are scribbles in a ledger still mostly blank. Every "that's odd" in a lab notebook, every model needs revision on a slide, every "we didn't predict that detail" whispered in a debrief adds weight to one side of something you cannot see, the balance between what we think we know about our sun and what it continues to withhold. Seen this way, AR4294 is less a warning and more an invitation. A reminder that the sun is not just a lamp but a laboratory. Magnetic reconnection, the snapping and rejoining of field lines, drives the flares you hear about in space weather reports, but it also shines in the auroras on Jupiter, in the jets erupting from young stars, in the violent outflows near black holes. Plasma turbulence, wave-particle interactions, the rise and fall of twisted magnetic tubes, these are universal processes, woven through the universe from the smallest scales to the largest. In one misbehaving sunspot group, with its strange rhythms and off-kilter flares, we get a controlled experiment we can watch from just one astronomical unit away, with instruments tuned to almost ridiculous precision. What looks from here like a moderate storm is, for physics, an opportunity. What NASA doesn't say in public is often not a secret at all. It is simply too intricate, too full of maybes and almost, to fit into words meant to reassure. The real story lives in the nuance, in the odd way AR4294's light curve hummed, in the quiet defiance of its flares, in the twisting path of its CME. All of this drifts back to a shared horizon, the edge of predictability. Meteorologists on Earth know that beyond a certain number of days, forecasts blur into possibilities. Tiny differences in initial conditions grow into storms in one path and sunshine in another. The weather remains bound by the laws of physics. Our ability to see which possible future will be realized fades. The same is true above the atmosphere in the sun's hot breath. In AR4294, flares erupted from places that had barely flickered before, while heavily stressed loops slept off their tension without drama. Recovery times from events varied in ways the models had not anticipated. Threads of cause and effect frayed. Our equations still tell us how energy can move in a plasma. They still rule what can happen. They do not, and maybe never will, give us perfect foresight into what will happen in a particular knot of tangled fields, at a particular moment, framed by 1,000 small fluctuations we haven't measured. Our forecasts live in that gap between can and did. AR4294 walked back and forth across that gap, reminding everyone that every confident number we print is a truce between complexity and approximation, not a promise. Underneath that technical uncertainty lies something softer and deeper. We comfort ourselves with the idea that the sun is a relatively calm star. We point to young, violent suns and other systems that spit megaflares many times a day and we say, ours is not like that. Ours is gentle. Ours is stable enough to cradle life. And it is, compared to many. But our direct window into its behavior is, in cosmic terms, the length of a breath. We have watched it with modern instruments for a few decades out of billions of years. We've caught hints of a few extreme events in the geological record and in scattered human reports. We've inferred the shape of its variability across centuries with clever tools. We have not seen every mode of behavior that might be possible. AR4294 was not a once-in-10,000 years event. It did not strip the atmosphere or silence the grids. But in its gentle refusal to fit perfectly into our categories, it tugged at a question that matters more than any one storm. What if what we call normal solar variability is merely one chapter in a longer, stranger book? What if, from time to time, the sun slips into patterns we have simply not yet had the privilege, or the misfortune, to witness with all our sensitive electronics in place? If that is true, then the anomalies around one sunspot group are not omens. They are the first faint lines of a later paragraph we will only recognize after we've turned more pages. And under all of this, quietly, there is the hardest question of all. How complete is our picture of the star that holds our orbit? We have equations for magnetohydrodynamics. We have models that mimic the solar cycle, with spots migrating, fields flipping, activity waxing and waning in a rough 11-year rhythm. We have probability distributions for flare sizes, scaling laws that relate magnetic complexity to storm risk. But between those abstractions and the blazing, spotted, flaring surface of the real sun is a gap made of all the details we don't yet resolve, and all the possibilities we haven't yet imagined. AR4294 existed entirely inside that gap. It did not violate the rules. It traced the edges of them, just far enough beyond our expectations to force pencil marks in the margins of textbooks and quiet updates in code repositories. What no one can easily say into a camera is what might matter most: that we are still very early in the process of turning the sun from a comforting symbol into a fully understood system. That we are, in many ways, making long-term plans for our civilization based on a dataset younger than some of the people listening to this. Above all of this, when you step outside at night and look up, the sky looks finished. The constellations hang where you expect them. The darkness feels smooth. The diagrams you've seen all your life, circles for orbits, icons for planets, a neat yellow disk for the sun, whisper that the cosmos, at least nearby, has been mapped. Events like those wrapped around AR4294 tug gently at that illusion. They suggest that the space between those clean lines is not empty, but filled with fields and flows we do not yet fully chart. That the sky over you is not finished. That you live under an unfinished sky. AR4294 did not shatter our confidence. It smudged it. It blurred the edges of words like safe and understood in the context of a star that can, without malice, without intention, thread a storm through the brittle, glowing skeleton of cables and signals we have wrapped around our world. We are not living under a sun that plots against us. We are living under a sun whose deeper moods we may not yet have seen, making intricate centuries-long plans in a room where one wall occasionally shudders, and no one can yet tell you in absolute terms how far that shudder can go. Eventually, AR4294 rotated away. The magnetograms quieted. New regions came into view. New forecasts were written. The name AR4294 slid from the top lines of internal reports into footnotes, then into archives. Most of the world never heard it at all. People will remember the days it touched, if they remember them, as nights when the aurora reached farther south, when flights took slightly different paths, when GPS glitched for a moment and then recovered. The sun from the sidewalk looked unchanged. But on servers and data centers, AR4294 remains. Sequences of strange magnetograms. Light curves with soft rhythms. CME trajectories that required second and third thoughts. Quiet adjustments to forecasting algorithms that will never mention its name in public. Somewhere, the star that lights your day has already written this scar into its own record. A tiny, turbulent knot in an ocean of fire that no one will ever see again except as numbers. And somewhere else, perhaps where you are, someone walks out of a doorway into gray morning light, feels the warmth on their face and looks up just long enough to squint. Above them, the sun is seething. Its invisible skeleton is twisting and untwisting, tying and untying knots in plasma 100 times taller than our planet. Some of that motion fits neatly into the equations on chalkboards and in code. Some of it does not. None of it asks us whether we are ready. The truest thing NASA isn't saying, not because it is hidden but because there is no easy way to say it, is that we are still growing into the knowledge that we live inside a system whose central engine is not fully mapped. We are small. We are trying. And the star that lights us is still patiently teaching. One day, another AR number will appear in a forecast. Another scar will rotate into view, its magnetograms feeling just a little bit wrong to the people who know how they should look. Maybe that region will pass quietly, adding a few more lines to the ledger and nothing more. Maybe it will coincide with a storm that writes itself into history books and infrastructure plans. Either way, the story will not begin that day. It is already underway in all the days like those of AR4294, when the sun quietly twisted just beyond our expectations and made us write needs more work in the margins of what we thought we knew. And as you listen to this, you might find that the next time your weather app shows you a little yellow disk for sunny, it feels different. Less like a cheerful sticker. More like a door. Behind that small, flat icon lives a globe of fire, marked now and then by scars like AR4294, storing and releasing energy so vast that your body cannot feel them directly until they have echoed through magnetic fields, through satellites, through grids, through devices, through decisions. You will still live your day. You will still board planes, plug in your phone, send messages that bounce off unseen reflectors in orbit. The world will hum as it always has under the stars in different light. But in some quiet corner of your mind, there may now be a new awareness. That above the blue, beyond the clouds, the star that holds your world in orbit is not finished telling you who it is. And while you sleep, it is still watching.